Okay, my name is Dr. Chris Bishop. I am the Director of Postgraduate Programs in Sport and the Program Leader for the Master's degree in Strength and Conditioning at Middlesex University. And I'm going to be talking to you today about interlimb asymmetry and the relevance or the importance of different calculation methods, why we probably for this type of data need to consider individual analysis, and the relevance and importance of longitudinal monitoring. And just before we crack on, just to say a big thank you to the FMPA and Kevin Paxton for the invite to come and speak to you today. So from a presentation outline perspective, just so you guys know what's coming up, we'll be looking at how we calculate interlimb asymmetry and the fact that we're going to provide some distinction between bilateral and unilateral tests would indicate, in our opinion, that it's not necessarily the same equation or formula that we would use. Understanding the limitations of group mean data, and as I said in the title, how that relates to individual data analysis and why that's probably so important for a metric like asymmetry. But really, individual data analysis has become quite vogue anyway in research in the last 10 years. Excuse me. The importance of monitoring asymmetry over time, but actually we're also going to be talking about not just that percentage raw absolute number, which is the magnitude, but we're going to be talking about the direction of asymmetry, which gives context to limb dominance, i.e. which limb performed better out of the two. And then we'll just round up the presentation with some parting thoughts about actually, is asymmetry really so terrible, given that when we think about it as a concept, inherently or intuitively, we think that an imbalance is something that we're supposed to correct, but actually it might not necessarily always be the case. So not really knowing everybody's sort of background or understanding or experience on this topic, I thought I'd just provide a few key operational definitions just to get everyone on a level playing field to start with. So the first one, as you can see there, relates to the difference in performance or function of one limb relative to the other. And that's not to be confused with intra-limb asymmetry, which focuses on any imbalance or difference within the same limb, which would be something like looking at hamstring quadricep ratios or the difference in strength between internal and external rotators at the shoulder joints on the same side. But for the purpose of this presentation, we're just going to be talking about differences in right and left leg, or dominant and non-dominant, or injured versus non-injured. Okay, so a between limb difference. As mentioned on the previous slide, when we think about the magnitude of asymmetry, we're just talking about that percentage value that is derived from looking at that between limb difference in test scores. So for example, if I jump 20 centimeters on my right leg, 18 centimeters on my left leg, I have a 10% difference or a 10% asymmetry, and that is the magnitude, that percentage value. When we talk about the direction of asymmetry, as said on the last slide, this is where we're trying to contextualize which limb performed better out of the two. So if we take that previous example I gave you again, we can say that although we have a 10% asymmetry, the direction of asymmetry favored the right leg rather than the left leg. Okay, and that is because when we perform jump testing, the desired outcome is the larger value. Okay, so we have a 10% magnitude favoring the right side, and that encompasses those middle two rows there in our table. And then lastly, we have something called the kappa coefficient, and this is a statistical method that looks at levels of agreement between two methods, but what it does is it removes any occurrence by chance that might be there. And whilst I don't want this to be a stats presentation, the reason I thought I would include it is because this is the statistical method we've used a number of times in the past to try and quantify the direction of asymmetry. So very simply put, if I have two test sessions, I'm not so much interested in how the magnitude of asymmetry differs using the kappa coefficient. I'm just looking at whether or not I still produce a larger jump height on my right leg in the second test session, or whether or not actually my left leg is now performing superiorly. So it's looking at that consistency and limb dominance between different test sessions. And whilst it might not be glaringly obvious why we should look at that now, we'll show you some interesting data from my PhD, which outlines how that can really differ between metrics and tests. Okay, so as promised in the content slide or the presentation outline slides, we're going to start off talking a little bit about calculations. And this is a little bit maths based, so bear with me. Now, at the start of my PhD lit review, I can't really tell you why I started looking at all these different mathematical formulas or equations. I just started noting them down in my big all-encompassing Excel spreadsheet. And what we noticed is that there's actually some quite subtle differences in the actual way that the formulas or the equations are set up. So, for example, if you can take the bilateral asymmetry index 1 and the bilateral asymmetry index 2, you can see that they're the same, except the second one just multiplies everything by 2 at the beginning. And really, when you look at some of these subtle differences in equations, and again, the top two are a good example of that as well. We've got non-dominant divided by dominant times 100, and then we've got 1 minus non-dominant divided by dominant times 100. So we've got a few subtle differences in some of these equations, and there isn't really any obvious reason as to why we should have them, or indeed whether or not it's relevant as to which one we should pick. But as you can see from the third column, I've highlighted in the grey box sort of hypothetical data of 800 and 700 newtons, when we're going to talk about hypothetically peak force as our metric of interest in this scenario. And we're just going to assume at this stage, and it is an assumption, that 800 newtons corresponds to the dominant leg or the right leg or the stronger leg, and 700 newtons corresponds to the left leg, the non-dominant leg, or the weaker leg. Now, that won't always be the case, but for the purpose of this hypothetical example, just bear with it. So as you can see from that third column, we actually get quite a vast array or range of different asymmetry outcomes once those 800 and 700 Newton values are input into each equation. So the first two to note are actually the same, okay? One is looking at symmetry as our reference point, 100% symmetry, and reports 87.5%. And the second one is actually looking at asymmetry, with 0 being our reference point. So 12.5 and 87.5 are actually the same thing. And then if we gradually go down that third column, we start to see some different numbers. So 13.3, 6.7, and then at the bottom, 4.2. So we've actually got, if we accept that 87.5% also means 12.5, we've actually got a range here of 4.2 to 13.3. So we've got almost like a range of 9.1%. And given that some of the literature historically has tried to indicate, and we'll talk more about this a bit later, that 10 to 15% might be a marker of injury, having a sort of 9.1% error range between mathematical formulas seems like a bit of a stretch and a bit of a problem. So if we jump forward, given that obviously the reason we're presenting this is to try and come up with some kind of a solution, what we've suggested is that if you're interested in calculating asymmetry from a two-legged test, like an isometric mid-thigh pull or a counter movement jump, remembering that in that grey box, our peak force is our metric of interest, then we think that either the symmetry index or actually the bilateral asymmetry index 1, which gives you the same outcome in this instance, these are the correct equations to use. And the reason being is because if we want to look at an imbalance between our right and our left, or our dominant and our non-dominant legs, we think that we should do that relative to the total output being produced. And that's because in a two-legged task, both legs are interacting together. So if we put those numbers into that symmetry index equation, what you get is 800 minus 700 divided by 1500, because actually in a two-legged task, the limbs, like I said, are not interacting independently. They're both working to produce 1500 newtons of force. And so actually we should probably interpret any asymmetry or imbalance relative to the total. However, for, excuse me, a unilateral test, we don't necessarily need to interpret any imbalance relative to the total output, because this time there is no ground reaction force contribution from the other leg, in which case we think that actually we should just be calculating the percentage difference the same way that we should be computing fractions in mathematics. So we don't now divide by 1500 newtons, we just divide by the larger value, which is exactly the same way that you would compute fractions. So symmetry index at the bottom for bilateral tests, and bilateral strength asymmetry for unilateral tests. Now, assuming that you accept that and adhere to our sort of anecdotal logic about different equations for different tests, it's important to understand that you're now just left with a percentage number, and it's not always entirely obvious what we should do with that. So there's some fantastic research in 2012 by Tim Excel, who works down at the University of Portsmouth, I believe. And very simply put, he suggested that an asymmetry might only be considered meaningful or real if that percentage value is greater than the variability score within each limb. And we can calculate that variability from the coefficient of variation. So if I now provide you, this is real peak force data from a bilateral counter movement jump, and it's actually from professional cricketers, not footballers, but the population is somewhat irrelevant to the point now being made. If we map on our coefficient of variation for peak force, what we get is coefficient of variation of 4% as that dotted red line, okay? And these individual bars, as you can see on that vertical axis column, represent the magnitude of asymmetry for these 16 professional cricketers. And like I said, this is for peak force during a counter movement jump. So the first thing to note is that the magnitude is highly variable for each athlete. You can see that athlete 14 is almost perfectly symmetrical, whereas athlete 11 and athlete 8, their magnitude is actually quite large, certainly relative to athlete 14. When we talk about whether an asymmetry is real, our interpretation of this graph is simply any blue bar that goes beyond or above that dotted red line would signify that this athlete's got a real asymmetry, and any athlete whose bar is below means that that asymmetry is inside the variance or the error of the test. Now, it doesn't necessarily mean that every athlete who has a blue bar above that dotted red line, we have to run a training intervention right away, but it does give you an understanding of being able to differentiate between signal and noise, with signal being asymmetry in this instance and noise being the coefficient variation. One other thing before we move on to the individual analysis part is to say, as useful as that is, every number here is a positive value, so it doesn't give us any understanding of the direction of asymmetry or limb dominance. So if we take the exact same scores, but now we map on the direction of asymmetry, and we say that any blue bar above 0 means that there was more peak force scored on the dominant limb, and any blue bar below 0 means that the non-dominant limb produced the larger peak force value. They're the same scores, remember, but now we've just got limb dominance applied to the graph. We map on our 4% coefficient of variation, and you get the same results, obviously, as the previous slide, but with greater context about who's producing more force on their dominant limb and who's producing more force on their non-dominant limb. Once we now have our equations at the bottom as a quick summary, these are what you would input into Microsoft Excel. I just want to highlight that for the unilateral equation, we would also add on something called an if function, whereby it basically says if the dominant limb scores less than the non-dominant limb, turn the value into a negative number, but don't change the magnitude. And that's because if we can't always guarantee that the dominant limb will always produce the larger value, then the denominator, which is the thing that we divide the difference by, that will essentially change the outcome. And we don't want that to happen, because that would kind of violate fundamental maths principles or fractions. Because if we think about it just logically and nothing to do with stats, when we're in maths class at the age of 10 or 11, we never learn 9 different ways to compute fractions. There's only one way to do it. Okay, so if we move on to the next part of the presentation now, which is where I'm trying to highlight the importance of group mean asymmetry being somewhat limited. So this is real data, okay, taken from a football academy this time, and every number you see on here is an asymmetry value, okay, for 10 football players. And we've got a strength test, we've got the unilateral isometric squat, we've got unilateral counter movement jump height, we've got 5:05 change of direction time, bearing in mind you can turn off the right and the left leg, so these are asymmetry numbers for total time. And then the change of direction deficit asymmetry, bearing in mind we also had 10-meter sprint in order to calculate the COD deficit from the 5:05 test. And the first thing to note is that if you just sort of scan vertically across any given metric, particularly peak force, jump height, and COD deficit, you'll see that there's a very large range in asymmetry values across the 10 athletes. So for peak force, athlete 7 is perfectly symmetrical, whereas athlete 4's got a much larger imbalance. If you now correspond, okay, across to jump height for those same athletes, athlete 7 was almost perfectly symmetrical in strength, but now has one of the largest asymmetries in jump height. Equally, athlete 4, who had the largest imbalance in strength, actually has one of the lowest in jump height. So we've got this really task-specific, highly variable concept going on here that doesn't necessarily transfer across to other tests. But the thing I've highlighted at the bottom in red is what I really want to focus on underneath the mean value. And that is to say, if you took peak force as a metric or jump height as a metric, you would probably expect the standard deviation to range from something like 5 to 25% of the group mean. However, in this instance, you can see on that bottom row, the standard deviation for asymmetry is huge. It ranges from about 61 to 87%. And what a really, really large standard deviation tells us is that we've got quite a high degree of within group variation in test scores. And like I said at the beginning, you can just see that from scanning the various ranges for different metrics. And we're going to kind of go into the longitudinal monitoring and trying to assess differences between time points now. And that will hopefully illustrate why this large standard deviation needs to be mentioned and why it might be a problem. So this is my second PhD study, actually. It was the first at the time to track and monitor the magnitude and direction of asymmetry in healthy athletes. Naturally, longitudinal monitoring had been done in injury-based research, but it hadn't really been done in healthy athletes. So this was done in elite academy football players. We tested the single leg counter movement jump and the single leg drop jump at 3 time points throughout a competitive season. And you can see we recorded 3 different metrics across both tests. We've got jump height, peak force, and propulsive impulse in the counter movement jump test, and jump height, ground contact time, and reactive strength index asymmetry during the drop jump test. So these numbers you see are group mean asymmetry values, and the second number in each box represents the standard deviation. So first thing to say is, again, if you look at the size of the standard deviation number relative to the first number, the group mean value, you can see that they're very large indeed. Okay, so for example, that first box for pre-season jump height for the counter movement jump, 9.58, probably represents about 85% of 11.19. So again, we've got this very, very, very large standard deviation value, and it doesn't seem to matter what test we choose, what metric we look at, or indeed what stage of the season, that number is always very, very large. If we now try and assess the differences between time points for each of those metrics, okay, we try to highlight this through the use of effect sizes. And at the bottom of each table, I've got an effect size scale for you for interpretation. And to save you a bit of time, I can tell you that the largest numbers across any of those 18 boxes occurs for peak force on that second row and ranges from minus 0.6 to 0.55. The minus obviously tells you that there was a reduction in asymmetry, and the positive number tells you that there was an increase in group asymmetry. Now, it's fair to say that all 18 numbers don't go higher than a small effect size. So all numbers are either trivial or small, and that kind of tells the story that asymmetry doesn't really change much throughout the season. So it's largely relatively consistent. But when the standard deviation is that high, and we know that that means there's such a large degree of variation within the group for scores, how could that possibly be the case? And we'll illustrate that on the next slide through a graph. The other thing, like I mentioned at the beginning, is we looked at kappa coefficients. And again, there's a scale at the bottom of each table, remembering that what we're looking at here is levels of agreement, okay, between time points. So simply put, if I jump higher or I produce more force on my right leg at pre-season, is it still that right leg that's outperforming the left leg at mid-season or end of season, or comparing mid-season to end of season? And if you take, for example, jump height for the counter movement jump, you can see that those levels of agreement range from fair to substantial. So not terrible overall. If you now take jump height for the drop jump test, you can see that we've got substantial levels of agreement mid to end of season, but actually pre to mid and pre to end are pretty poor. Those numbers have got much, much lower. And that kind of means that the direction, or the limb that's producing the most force, the limb that's jumping higher in this instance, because that's the metric we're looking at, actually that's swapping sides quite a lot from time point. So it's probably easier to illustrate this on a graph. So I'll show you two, and this will look at jump height. The first one will focus on the single leg counter movement jump, and the second one, will focus on the single leg drop jump. So across the entire season, we managed to get 18 players consistently through all three testing sessions. And, you know, no surprises that we started the season with nearly double that. But as is the case in football, players got injured and went to different clubs. So we actually only got 18 players through the entire season. So things to note on this graph. Well, the size of each individual bar varies at each time point for each athlete quite a lot. And actually, if we focus on that kappa coefficient statistic, what we're trying to look at in this graph is, regardless of whether or not the bars are above 0 favoring the dominant leg or below 0 and favoring the non-dominant leg, how many times do you see 3 bars pointing in the same direction? And the answer is, if you count along each individual athlete, you'll see 13 times, or 13 athletes show consistent limb dominance characteristics throughout the entire season for unilateral counter movement jump height. So athlete 1's a good example. You see all 3 bars are above 0. Same with athlete 2. And then if you scroll across, you get to athlete 7, who actually starts jumping a bit higher on their dominant limb at the start of season. But throughout the season and at the end of season, that limb dominance has switched sides. Same with athlete 8. They actually favor the non-dominant limb quite heavily at the start of the season. But by the end of the season, the dominant limb's completely taken over. So we've got 13 out of 18 players showing consistent limb dominant characteristics throughout the season. If we now compare that to the unilateral drop jump for the same metric, jump height, the answer is actually only 8. So we're now getting much more or much greater fluctuations in sort of natural jump height performance variability, I guess is what I would call that. It's a bit of a mouthful. But I guess the point of illustrating this is to say that, you know, not every test will show you the same information. It's a highly variable concept. And if we want to be able to tease out or draw out any meaningful information about asymmetry, given that the magnitude varies so much from person to person, and given that each test probably tells you somewhat different information, we probably need to do our assessments on an individual basis. We probably need more than one test because, you know, it's very, very rare for one test to tell you the same thing when we're looking at imbalances. And I think that we need to have an appreciation that because this is such a variable concept, we should also consider trying to determine whether or not asymmetry is larger than the noise of the test. So relate our findings back to the coefficient of variation. And maybe then we might start to have a better understanding about what's meaningful, what's real, and what's just natural fluctuations in performance throughout the season. So last sort of 2 or 3 slides now, which is to just round off some parting thoughts on the topic. So I think we need to give a bit of credit to 2 people on this. I think the first time I saw something like this was actually from Eamon Flanagan on Twitter a few years ago. And something similar is included in a publication by Tom Dos Santos in the NSCA Strength and Conditioning Journal, where we can, broadly speaking, classify athletes into these 4 categories. But to sort of play devil's advocate about our sort of intuitive thought process about correcting an imbalance, if we take a sport like sprint cycling, whereby one of the most important determinants of performance is mean power, I've presented you 3 sort of hypothetical athletes here. You can see that athlete A has very much the largest asymmetry, much larger than the other 2 athletes, but the total wattage is higher than the other 2. So if I started asking myself, which athlete would I prefer to be in this scenario, given that sprint cycling doesn't have any sort of direct impact per se, as you would do with sort of running and ground reaction forces, I'm not sure I'd care so much in this instance if my athlete had a 20% imbalance, if we know that mean power is one of the key determinants for sprint cycling performance, and athlete A produces the largest total mean power. So I think in this instance, I just wouldn't be so concerned about the imbalance per se, but rather if this athlete is strong and asymmetrical, I still think they probably win the race because they produce the total amount of wattage, the highest total wattage out of the 3. And that kind of leaves us next to this concept of, you know, how should we interpret asymmetry if we see it then? And this is a sort of concept spoken about by Sean Maloney, who did a fantastic review on the topic in 2020. And he calls it, he sort of coined the term a window of opportunity, which I think lots of others have used before, but he definitely used it within the context of asymmetry in his review specifically. So if we look at athlete 1, first of all, you can see that if we just look at the blue bars only for athlete 1, you can see that the dominant limb produces more peak force in our hypothetical metric or test here. In session 2, the red bars for athlete 1, actually now the non-dominant limb is producing more force. And then in session 3, the grey bars, it's swapped back again. So we're getting these fluctuations in performance between limbs. If we now look at athlete 2 across those 3 test sessions, we can see that we've got a very definitive and very consistent dominant limb outperforming the non-dominant limb. Athlete 3, similar to athlete 1, we've got these fluctuations. So it's in this instance, it's probably not athlete 1 or athlete 3 that I'm that concerned with. Maybe athlete 2, who is showing consistently underperforming limbs, or one limb relative to the other. Maybe I would view this as actually, it's not so much the percentage value that's a problem. Maybe it's just that the non-dominant limb needs a bit of work to improve its limb capacity, because it's probably not much that can go wrong from giving a limb extra capacity. Okay, penultimate slide now. This is a narrative review that I wrote, again, for the NSCA Strength and Conditioning Journal about a year ago. And it was kind of a bit of an opinion piece, really, about whether or not these different thresholds of 10% or 15% can be used in sort of day-to-day practice. So as mentioned earlier, a lot of injury-based research has tried to suggest or indicate that 10 or 15% might mean that athletes are at a greater risk of injury. But if you dive into that research in a bit more detail, what you end up finding is that a lot of them have made that suggestion just based off of citing someone else's work rather than their own specific empirical findings. If you then dive into some of the references that have been used and go back to some of their research in the late 80s and early 90s, actually some have suggested that 15% is a marker for increased injury risk, because that's the normative value that's been suggested from a single test across a healthy population of about 1,000 people. So it's not even that was a percentage value that was shown to be to provide a risk of injury. It was, that's the value that's normative data in healthy people, which seems a little bit of a flawed concept, really. I also think, and this is probably going off of sort of experience of having well over 200 data sets, we know that if you take multiple metrics for any given test, like we did in our study, and I showed you that longitudinal study earlier with the blue, red and green boxes, you don't get the same asymmetry value for different metrics in the same test. So if I monitor jump height, ground contact time and reactive strength index, they all produce different asymmetry values for each subject, and naturally then different mean values for the group. So again, I think it's probably a somewhat flawed concept to say that if 10% is my marker for injury, jump height's my risk of injury, but ground contact time and reactive strength isn't. That seems quite a flawed concept, given that they're all kind of the same, they're all different metrics for the same tests, but actually they just give us an understanding of outcome and strategy. So just in conclusion, if we think about what we can take away from this presentation, be sure to think about the most appropriate formula to calculate asymmetry, whether you're testing bilaterally or unilaterally. Not enough studies have probably been conducted with repeated measures designs and longitudinally. There have been a couple more studies that have been conducted looking at asymmetry across the course of a competitive season, and they've largely shown the same thing, really, as the study presented earlier today. As kind of alluded to with regards to the standard deviation, asymmetry is a ratio number, okay, and that makes it quite noisy as a concept. So that means that, and I know I'm flogging a bit of a dead horse and saying the same thing here, but that probably means we need to monitor on an individual level. And if you have to monitor something on an individual level, we need a way of making sure that that's provides us with meaningful information, and comparing that asymmetry value to the coefficient of variation can help us do that by differentiating between the signal and the noise. And we talk about differentiating between the signal and the noise quite a lot in performance testing data. So in reality, asymmetry should be no different. And then lastly, because that standard deviation is so high and often precludes us from finding any meaningful differences at the group level, we might want to try and account for some of that variability by looking at consistency in limb dominance or the direction of asymmetry. And for anyone that's interested, you can go to this link where I've done a 12-minute YouTube video on how you can calculate that kappa coefficient in Microsoft Excel, because you don't actually need a stats software program to do it. You just need to create a number matrix in Excel and you can calculate it yourself. Thanks very much for listening and hope you enjoyed it.